Hello dear students, welcome back to school, welcome back to class. Here are the objectives of our lesson for today. At the end of today's lesson, all the students in this class should be able to state Faraday's first law of electrolysis. At the end of the lesson, all of you in this class should be able to express Faraday's first law of electrolysis mathematically. At the end of today's lesson, all of you in this class should be able to state the relationship between Faraday and number of moles of electron. At the end of today's lesson, you should all be able to give examples of monovalent, divalent, and trivalent metals. And at the same time, all of you at the end of the day should be able to solve problems using Faraday's first law equation or formula. Let's begin with the brief history of Michael Faraday. Michael Faraday was born in 1791 and died in 1867 at 76. He is an English scientist and was the first person to describe electrolysis in 1833. This man came from a very poor home. The father is a blacksmith, but he worked very hard to become one of the greatest scientists in history. This man is among the inventor in the second industrial revolution. In 1831, he invented what we refer to as the first electric generator, and the symbol that we use in electrolysis, which is Farad, was named after Michael Faraday, Farad, in honor of him, with the symbol capital letter F. So this is Michael Faraday, the one you have been hearing about. Here is Faraday's first law of electrolysis, which states that the mass of the element deposited during electrolysis is directly proportional to the quantity of electricity passing through the electrolytes. We can express this mathematically, and to do that, we have mass directly proportional to Q, which is the quantity of electricity. Mass is measured in gram and quantity is measured in coulombs. But quantity of electricity is equal to the product of current and time. And current is measured in amperes, the time is measured in seconds. So if quantity of electricity is equal to the product of current and time, then we can substitute IT for Q in this equation here. So if we substitute IT for Q, then we are going to have mass directly proportional to the product of current and time. So, but we cannot do anything with this formula. We need to introduce proportionality constant so that we can put equal to sign. So the constant we are introducing now is this letter Z that you have here. So mass is equal to the constant, current, and time, the product of the three of them. Of course, we can make any of these three variables subject to the formula. So if we decide to make the constant subject of the formula, then the equation will then look like this. We then have the constant, which is Z, to be equals to mass divided by the product of current and time. And we can as well look for the reciprocal of the constant. Reciprocal of a constant is, when you hear reciprocal, it's just 1 over that particular number. 1 over Shola is reciprocal of Shola. 1 over Shade is reciprocal of Shade. So reciprocal of the constant is 1 over Z. And to do that, you make the denominator here the numerator, and you make the numerator the denominator. So it will be the product of current and time over the mass. And don't forget that the product of current and time is equals to quantity of electricity passed. Therefore, we can substitute Q for IT here. So what we are saying here is that the reciprocal of the constant is equals to IT over M or Q over M, where Q is quantity of electricity passed and M is mass deposited. Let's look at the following examples. Example number 1. Determine the quantity of electricity passed if a current of 0.4 amperes flows through an electrolyte for 30 minutes. How do you solve this? Let's look at the solution. By the way, if I may ask, which formula are you going to use to solve this question? Yes, that is going to be Q equals IT. Why are we using Q equals to IT? We have been given the current to be 0.4 amperes and we have been given the time to be 30 minutes, but we have to convert it to seconds because time is measured in seconds. So to convert time to seconds, what you need to do is to multiply by 60 and that will give us 1800 seconds. So you bring the values together, that will be 0.4 times 1800 and that will give us the quantity of electricity to be 720 coulombs. Let's look at another example. Example number 2. Calculate the time it will take 9600 coulombs of electricity to be produced when a current of 1.0 ampere is used. So which formula are we using for this? Of course, we are using the same formula. We are going to use the same formula we used to solve the first example, which is what? Q equals IT. But in this case, we have been given the quantity to be 9600 coulombs and we have been given the current to be 1.6 amperes. So we are looking for time. So we can make time subject to the formula. So how would the equation look like? It will look like what? T equals Q over I. And then divide 9600 coulomb by 1.6 amperes. And that will give us what? The time to be 6000 seconds. This is very important for everybody to know. We are looking at the relationship between Faraday and number of moles. 1 Faraday is equal to 96,500 coulomb, and that is equal to 1 mole of electron, and that is also equal to 6.02 exponential 23 electrons. So what are we saying? What I'm saying is that the quantity of electricity required to discharge 1 mole of electron is 96,500 coulomb. This quantity of electricity is what we refer to as 1 Faraday. So 1 Faraday is equal to 96,500 coulomb. And 1 Faraday discharge 1 mole of electron, like I've told you at the top here. So that 1 mole of electron is numerically equal to 6.02 exponential 23. So take note of this, everybody. Monovalent metals and monovalent diatomic elements. Let's start with the monovalent metals. These are metals that carry just one charge, and the example of those kind of metals are silver. So silver is a monovalent metal. It carries a charge and it will gain 1 electron to produce a metallic silver, a neutral silver. So we have 1 mole of silver ion gaining 1 mole of electron to form 1 mole of silver. So the number of mole of electron is equal to the number of Faraday, which I told you. So 1 mole of electron is equal to 1 Faraday, and that is equal to 1 mole of the silver. So 1 Faraday is equal to 96,500 coulomb, and 1 mole of silver is equal to 108 gram. That is the mass. Another example is sodium ion. Sodium ion, we gain 1 electron to form a neutral sodium. So we have 1 mole of sodium ion produce a metallic sodium, 1 mole of a metallic sodium. 1 mole of electron is equal to 1 Faraday, and 1 Faraday is equal to 96,500 coulombs of electricity. 1 mole of sodium is equal to 23 gram. So, but notice that 1 mole of an element is equal to the atomic mass of the element. So 1 mole of sodium is equal to 23 gram. If it is 2 mole, that means it's going to be 23 gram times the number of mole. That is just an example. So let's look at another, the one of monovalent diatomic. These are elements that carry a charge but are diatomic in nature. So we have examples of hydrogen, fluorine, iodine, chlorine, and this ones requires 2 Faradays to deposit 1 mole. So example, we have hydrogen ion. So this is 2 moles of hydrogen ion gaining 2 moles of electron to form hydrogen gas. So what do we have? 2 moles of hydrogen ion, 2 moles of electron, 1 mole of hydrogen gas. That's 2 mole. The number of moles of electron is 2. That's to tell us that it will require 2 Faraday. So but the 1 mole of hydrogen gas is 1 gram. So but the number of hydrogen atoms that we have here is 2. So the number of hydrogen atom times the number of the atomic mass of 1 hydrogen atom. So now that we have 2 hydrogen atoms, we multiply the atomic mass by the number. So 1 Faraday is 96,500. So 2 Faraday will be what? 2 times 96,500, and we have the atomic mass of hydrogen gas to be 2. Okay, another example is chlorine, which that is from chloride ion. So we have 2 moles of chloride ion losing 2 electrons to form chlorine gas. This is 2 moles forming 1 mole of chlorine gas by losing 2 moles of electron. So 2 moles of electron is equal to 2 Faraday, and the atomic mass of chlorine is 35.5. Here we have 2 chlorine, so that will be 35.5 times 2, and that is going to give us what? 71 gram of chlorine requires 2 times 96,500 coulombs of electricity. Divalent metals and divalent diatomic elements. Let's look at divalent metals first. These are elements that carry just 2 charges, and the example is we have copper 2 ion. Copper 2 ion, we gain 2 electrons to form a metallic copper. That is 1 mole of copper. 1 mole of copper ion, we gain 2 moles of electron to form 1 mole of metallic copper. So 2 moles of electron is equal to 2 Faradays, but 1 mole of copper is equal to 63.5 gram. So 1 Faraday is 96,500. 2 Faraday will be what? 2 times 96,500. What it means is that 63.5 gram of copper will require what? 2 times 96,500 coulombs of electricity, which is what? 193,000 coulombs. Another example is that of calcium ion. So this is calcium ion, and by the way, you can see 2+, so it's a divalent metals. So calcium ion, we gain 2 electrons to form a metallic calcium. So we have 1 mole of calcium ion gaining 2 moles of electron to form 1 mole of calcium. So 2 moles of electron is equal to 2 Faradays, and 1 mole of calcium is equal to 40 gram. So what do we then have? A Faraday, or 1 Faraday, is 96,500. 2 Faraday will be what? 2 times 96,500 coulombs. Let's look at the divalent diatomic. These are elements that are diatomic in nature but carry 2 charges. So we have examples of oxygen. So we have 2 moles of oxygen producing oxygen gas by losing 4 moles of electron. So this is 2 moles, 1 mole of this and 4 moles of electron. So the atomic mass of oxygen gas is 16. Atomic gas of oxygen rather is 16, but there are 2 oxygen atoms here. That will be 2 times 16, and here we have 4 moles of electron, which is equals to 4 Faradays. So 4 Faradays will be 4 times 96,500 coulomb, and it gives 32 grams. So what it means is that 32 grams of oxygen requires 386,000 coulombs of electricity. For trivalent metals and trivalent diatomic elements, let's look at the trivalent metals. These are elements that carry 3 charges. So we have example of aluminium. So aluminum is a trivalent metal and it will require 3 Faradays. How? 1 mole of aluminum ion we gain 3 moles of electron to form 1 mole of a metallic aluminum. But 3 moles of electron is equal to 3 Faradays and 1 mole of aluminum is equal to 27 grams. So what do we have? 1 Faraday is 96,500 coulomb. 3 Faraday will be what? 3 times 96,500 coulomb. And what this means is that 27 grams of aluminum requires what? 3 times 96,500 coulomb of electricity. You can do this calculation by yourself. That is not difficult at all. But for trivalent diatomic elements, these are elements that are trivalent but are diatomic in nature. So we have nitrogen. So nitrogen here, this is nitrogen ion. With 2 moles of this nitrogen ion, we produce 1 mole of nitrogen gas by losing 6 moles of electron. So, but atomic mass of nitrogen is 14, but there are 2 nitrogen atoms here. That will be 2 times 14, and 6 moles of electron is equal to 6 Faradays. So what do we then have? 2 times 14 will be 28 grams, while 6 Faraday will be 6 times 96,500 coulombs of electricity. Let's look at some other examples. Let's look at this question. How many moles of electron are required to deposit 112 grams of iron if the atomic mass of iron is 56 and 1 Faraday is equal to 96,500 coulomb? How do we solve this? We can use equation method. But first of all, you need to write the equation of the reaction. Iron to iron, we gain 2 moles of electron to form metallic ion. 1 mole of iron, we gain 2 moles of electron to form 1 mole of metallic ion. So 2 moles of electron is equal to 2 Faraday and 1 mole of iron is equal to 56 grams. So what do we have? 2 Faraday is equal to what? 2 times 96,500 coulomb, because 1 Faraday is 96,500 coulomb. So what I need to do is to write it out. From this equation, I can see that 56 grams of iron requires 2 moles of electrons. And in the question, we are given another mass of iron to be 112. And we are asked to determine the number of moles of electron that it requires. So what I need to do is just cross multiply. 112 grams goes against 2 moles of electron. 56 grams goes with S mole of electron. So make X subject to the formula because that is what we are looking for. And then you have what? 112 grams times 2 moles divided by 56 grams. Gram cancel gram, and you can just say 56 here 1, 56 in 1, 1, 2, 2. 2 times 2, 4 moles. So the number of moles of electron that is required to deposit 112 grams of iron is 4. Let's look at another example. Example number 2. What quantity of electricity will liberate A. 0.125 mole, B. 1.12 dm cube of oxygen gas during the electrolysis of dilute sodium chloride solution? 1 Faraday is equal to 96,500 coulomb per mole. So how do we solve this? Can you solve it, or I should solve it for you? You need to learn to do things by yourself. So what is going to be the solution? Remember, in the electrolysis of dilute sodium chloride, which we have done before, at anode, hydroxide ion was discharged and oxygen gas was liberated. You remember that? We have done it before. So this is the equation of the reaction, and from here we can see that 4 moles of hydroxide ion, we liberate 1 mole of oxygen gas and we lose 4 moles of electrons. So 1 mole of oxygen is equal to 1 volume of that oxygen, and 4 moles of electron is equal to 4 Faraday. So the volume of a gas at STP is equal to 22.4. So 1 volume of oxygen gas at STP is 22.4 dm cube. If it is 2 moles, it will be 2 times 22.4, but here we have 1 volume. So 1 volume is equal to 1 mole, and that is equals to 22.4 dm cube. So what I need to do is to say that 4 Faraday, which is 4 times 96,500 coulombs of electricity, liberates what? 1 mole of oxygen gas, as you can see here in this equation. But we are to calculate the number of the quantity of electricity that will liberate the number of mole of oxygen that has been given in the question, which is what? 0.125 mole of oxygen. So what I did was to cross multiply. So this with this, and x goes with 1 mole. So what do? I have 4 times 96,500 coulomb times 0.125 divided by 1, and that then will give you what? The quantity of electricity that is required to liberate 0.125 mole of oxygen gas is what? 48,250 coulombs. Example number 2, where we are asked to calculate the quantity of electricity that will liberate 1.12 dm cube of oxygen gas. So we have 22.4 dm cube of oxygen gas liberated by 4 times 96,500, which you can see here. So if the volume from the equation is 22.4, and we're given another volume to be what? 1.12 dm cube, and we are asked to calculate the quantity of electricity that will liberate this volume. What you have to do is to cross multiply. 1.12 goes with 4.96,500 coulomb, while 22.4 goes with y. So make y subject to the formula. You have what? 1.12 dm cube times 4 times 96,500 coulomb divided by 22.4 dm cube. So dm cube will cancel dm cube, and then you have what? Your numerator, that's 1.12 times 4 times 96,500 is going to give you what? 432,320 divided by 22.4, and that is going to give you what? It's going to give you 19,300 coulombs. Here is the alternative method to solve this problem. Here we have CF over M, which is a constant value for an element. But you will recall that under the mathematical expression, we already have 1 over Z to be equals to IT over M. But CF over M is equal to 1 over Z. And therefore we can substitute CF over M for I over Z in this equation, which will give us what? 1 over IT over M equals CF over M. So we can then rearrange this equation, and by rearranging it, it's going to give us what? IT over CF equals to M over M. By the way, I is current, T is time, C is the charge on the element, F is Faraday, M is mass, while capital letter M is molar mass or atomic mass. So here they are. So mass is measured in gram, molar mass is measured in gram per mole, but atomic mass does not have units. Current is measured in ampere, time is measured in seconds, charge of the ion. Let's use the alternative method to solve some problems. Let's look at this. Calculate the mass of zinc deposited when 25,000 coulomb of electricity is passed through an aqueous solution of zinc tetraoxosulfate 6 for 30 minutes if the atomic mass of zinc is 65 and 1 Faraday is equal to 96,500 coulomb per mole. How do we solve this question? The first thing is to write the equation. zinc is a divalent metal. It will gain 2 electrons to form a metallic zinc, and that means we have 1 mole of zinc gaining 2 moles of electron to form 1 mole of metallic zinc. So we have 2 moles of 2 moles of zinc to be equals to 2 Faraday, while 1 mole of 2 moles of electron is equals to 2 Faradays, I beg your pardon, while 1 mole of zinc is equals to 65 gram. So 2 Faraday is equals to 2 times 96,500 coulomb, that is 193,000 coulomb. You can punch your calculator, you get that. So we have 193,000 coulombs equals to 65 gram of zinc. That is 65 gram of zinc requires 193,000 coulombs of electricity. So, but now that we have been given another quantity of electricity, the question is, what mass of zinc will that deposit? So you can just cross multiply, and what will that give you? We have mass over molar mass to be equals to what? The product of current and time over the product of charge and Faraday. So, but don't forget that we have already defined Q to be equals to the product of current and time. So we can substitute Q for IT in this equation. And to do that, what are we then going to have? We will then have our mass to be equals to molar mass or atomic mass times current times time divided by charge times Faraday. Or we can say, since Q is equals to IT, we can substitute Q for IT here, and then we have MQ over CF to be equal to the mass of that element. So then what is going to be the solution? Let's see, mass. So we have the atomic mass, or if you like relative atomic mass of zinc to be 65 gram per mole, and the quantity of electricity, the new quantity of electricity is 25,000 coulomb. We have the charge to be C. Charge is 2 and Faraday is 96,500 coulomb per mole. So mole cancel mole, coulomb cancel coulomb, and then what do we have? We have 1,625,000 gram divided by 193,000, and that will give us the mass to be what? 8.4 gram. Or alternatively, we can do it this way. We can say that 65 gram of zinc requires 193,000 coulomb of electricity. S gram of zinc requires what? Requires 25,000 coulomb of electricity. So what is X? X is what? 65 gram times 25,000 coulombs of electricity divided by 193,000 coulomb of electricity. Coulomb cancel coulomb, and then what do we have? We have 1,625,000 gram over 193,000, and that gives us the value of our X to be what? 8.4 gram. So if you use this method, which is the equation method, you get the same thing even when you use the alternative method that we are talking about. Let's consider another example. Look at this question. We are to calculate the time required to deposit 56 grams of silver from a silver nitrate solution using a current of 4.5 ampere. How do we solve that? Write the chemical equation first. So the chemical equation will be what? Silver ion, which is a univalent, or if you like call it monovalent metal, we gain 1 electron to form a metallic silver. So 1 mole of silver, we gain 1 mole of electron. 1 mole of silver ion, we gain 1 mole of electron to produce a metallic silver. So here we have 1 mole of electron to be equal to 1 Faraday, while 1 mole of a metallic silver to be equal to 108 gram. So 1 Faraday is equal to 96,500 coulomb. And note this, that the number of mole is equals to mass over molar mass. And to get the number of mole, we just have to divide the mass that I'm given in the question here by the atomic mass, or if you like, molar mass of silver that we've been able to get from the equation here, and that will give us the number of mole to be what? 0.519 mole. But don't forget that the number of since in our previous work we have already defined mass over molar mass to be equal to Q over Cf, and we are saying that mass over molar mass is equal to number of mole. Therefore, we can substitute number of mole for mass over molar mass, and we'll have another equation to be what? Number of mole equals to quantity of electricity divided by Cf. And if that is the case, what do we have? We've been able to get the number of moles to be 0.519, but we don't know the quantity of electricity that is required for that number of mole to be produced. So we have, but in the equation we have 1 mole of silver requiring 1 Faraday, which is 96,500 coulomb. So make Q the subject of the formula, and we're going to have this 96,500 coulomb times 0.519 mole, and that will give us what? 50,083.5 coulombs. But don't forget that Q is equal to IT, that we have seen many times. So if Q is equal to IT, and we've been able to get our Q here to be what? 50,083.5 coulomb, and the current has been given in the question to be 4.5. So to get our time is not going to be difficult. Make time subject to the formula, and you are going to have what? 50,083.5 coulomb divided by 4.5 amperes. Then the time is going to be what? 11,129.67 seconds. But in case you are asked to leave your answer in minutes, what you need to do is to divide that value by 60, and that will give you 185.5 minutes. If you are asked to leave it in an hour, what do? Divide this by 60, and that will give you what? 3.1 hours. What have we learned in our lesson today? First, we have been able to state Faraday's first law of electrolysis. We've been able to express Faraday's first law of electrolysis mathematically. We've been able to state the relationship between Faraday and number of moles of electron. We've been able to state examples of monovalent, divalent, and trivalent metals. And we've been able to do some calculation using Faraday's first law equation, or if you like, formula. Here is my email address for your comments, for your advice, for your questions. My name still remains Ibukunolu Ademola. Thank you.